My name is Kriti and I'm taking care of applications for liquid chromatography portfolio for Agilent. Today I will be talking about fundamentals of polarimetry, refractometry and fluorimetry and their applications. So let's start with the first topic, polarimetry. So basically polarimetry is an instrumental technique that measures the rotation of plane polarized light in optically active compounds. Normally, this polarimeter can find out or can tell us the values of concentration and physical properties of the solution, and the solution must contain an optically active compound. From this measurement, different parameters such as specific rotation, concentration, sugar content, and purity can be determined. So there are several applications in various industries for polarimeter. Okay, so let's start with the most important topic. What exactly is polarization? Now, according to wave theory of light, an ordinary ray of light is considered to be vibrating in all planes, especially at right angles to the direction of propagation. Now, if this light is passed through a Nicol prism or a polarized filter, the emergent ray has its vibration only in a single plane. Such a light is called as polarized light, and this phenomena is called as polarization. Now, this is normally exhibited by optically active compounds, right? And those compounds are called as enantiomers or chiral compounds. According to the direction in which the light is rotated, the enantiomer can be referred to as dextrorotatory or levorotatory. Now, let's discuss what optical activity basically means. So, it's a very basic principle of using a polarimeter. Now, molecules which are having mirror image geometries are called chiral. However, there is a fix in this that you cannot superimpose these geometries. If you see this image below, even though both these hands are mirror images, it is not possible to superimpose. They are asymmetrical. Whereas if you see the image on the right hand side, if you see this flask, it is symmetrical in nature and it can be easily superimposed. Hence, it is also called as handedness, right-handedness, left-handedness, instead of calling them dextrorotatory or levorotatory. Now, chiral molecules are typically called as enantiomers, like I already mentioned. And the common examples would be organic molecules and biomolecules, such as starch, sugars, flavors, essential oils, a lot of active pharmaceutical ingredients, amino acids, and there are a lot of other examples of optically active compounds. Now let's talk about the working principle. Uh, Basically, a polarimeter consists of a light source. Light source could be your light emitting diodes, or commonly called as LEDs. Now this LED would produce a beam of ordinary light, and it would obviously propagate in all the directions. It would vibrate in all the directions. Now the light first passes through a polarizer. In order to obtain a defined orientation, we need to keep a polarizer or a polarized filter, okay, to define the orientation of the plane polarized light. Once the light is in a of light, okay, which is this second polarization filter. The polarimeter normally rotates the first polarizer until the photoreceiver measures a transmission minimum. That means there is no light now. The photoreceiver sees no light. That is what transmission minimum means. Now, if the sample is optically inactive, the polarizer and analyzer would be perpendicular to each other. If the sample is optically active, the polarimeter will rotate the polarizer until the plane of plane polarized light behind the sample is again perpendicular to the polarization, the plane of polarization. The resulting degree of rotation is a direct measure of optical rotation of the sample. Okay, and a correct wavelength for measurement is precisely selected normally for such analysis. Let's talk in detail about the measuring principle. So this is an image of a analyzer, the polarizer basically, the second polarizer. Okay, we can see it from the front side and imagine that behind this filter you have your light source. Suppose we rotate this second polarizer such that the maximum light can pass through. This will give us a polarization angle, which can be compared to the old angle, the earlier one, and this difference will basically give us the optical rotation. But this is not a precise way to calculate because it is difficult to compare with no light, with less light and more light. And it's easier to compare where there is no light and minimum light. So let's assume that we rotate this polarizer filter till there is no light transmitted. Then what happens? This is measured as transmission minimum. Now, by achieving such a value of transmission minimum, we can add plus 90 degree to precisely determine the optical rotation of the sample. So whatever is the angle of transmission minimum, we need to add plus 90 degrees to that to determine optical rotation. So normally in polarimeters, your transmission minimum is measured, not the first phenomena that I talked about where we measure low light and slightly more light, better light. Now, what information that you can get from a polarimeter? Okay, so this measured value in a polarimeter is called as optical rotation and it is measured as an angle, alpha degrees of optical rotation. From this angle, we can find out the concentration of a sample. Maybe it could be a unknown concentration in a sample where we know the specific rotation of the substance, sugar concentration for known specific rotations again. We can also find out the specific rotation wherein I am aware of the concentration. We can find out the purity in combination with a refractive index, and also lastly user defined scales. So basically you can find out what is the specific rotation of a particular standard compound. Let's talk about what is a specific rotation. So basically optical rotation depends on the number of molecules the light beam will meet. Okay, the more the molecules, the more the light will rotate. So we define a certain sample density as, for example, 1 gram per 100 ml, as well as the wavelength of light that passes through the sample must be known and must be constant. The optical rotation measured under these conditions are specific rotation. We also define a fixed path length of the flow cell. So we know the concentration and we fix the path length at 100 mm. Another influential condition is temperature. Since the density of the molecules will change under different temperature conditions due to thermal expansion, so we need to also keep it in a controlled temperature. We also need to consider the wavelength of the light beam we send through the sample. So this way we can accurately determine the sample specific rotation value. So at what Utmost care must be taken with concentration, length of the sample cell, and temperature. These are the three combination of factors that affect or will affect your end results. Now let's discuss of applications for polarimeter. Generally, it is used in quality control, determine purity of pharmaceuticals, sugar, starch-based products. There are several applications in QC. They are also temperature control polarimeters can also be used to determine some gelling behaviors. Most importantly, since the samples are not destroyed by this technique, it can easily be used to measure the purity of expensive raw materials, okay, such as essential oils and in perfume production. Okay, so let's discuss industry wise what would be the applications of a polarimeter. In pharmaceutical industry, purity control, content determination, determination of stereochemical composition is of utmost importance because sometimes there would be active pharmaceutical ingredients of which one enantiomeric form is harmful to the body and the other one is not. So it is extremely important. Commonly analyzed substances in the pharmaceutical industry would be sugars, amino acids, vitamins, steroids, antibiotics, painkillers, amphetamines, etc. The governing authority, the authority or the US Pharmacopoeia, BPJP, these are the governing authorities that publish the methods that provide the standards of what is the pass-fail criteria, the system suitability conditions, etc. For chemical industry, again, purity control, concentration can be determined. In process, uh, in chemical processes, in process analysis can be done during production. And commonly analyzed substances would be biopolymers, synthetic polymers, various hydrocarbons. And again, here the authority providing the standards would be AOAC, OIML, ASTM, etc. Food and beverage industry, again, purity, quality control, determination of concentration of sugar, starch, lactic acids in food, in sugar in honey, sugar composition in honey, lactose in milk. These are some common applications in food industry. It is also used in sugar industry. So in sugar mills and plants where sugar is manufactured. So raw material is tested. In preliminary tests can be done. Intermediate tests and end products also can be tested. So sugarcane, beetroot, beet pulp, molasses, refined sugars, these can be analyzed in sugar industry. And here IUCM SA, which is also called as I, ICUMSA. So this is a governing authority which basically provides a standard system suitability criteria for sugar industry. And manufacturers of aromas, like I said, that costly or precious samples can easily be tested for quality control of raw materials and additives without destroying the sample. So this is a very good technique for analysis of essential oils such as orange, lavender, lime, peppermint, etc., etc. Okay, so in perfume industry, it has a very good application. Let's talk about the next topic, which is refractometry. So basically, before talking about what refractometry is, we should know what a refractive index is. Okay. So basically, the ratio of speed of light in a vacuum or air to the speed of light is a specific medium is called a refractive index. Okay. Every material with which light interacts has a refractive index. Now, this constant dimensionless number describes how fast will light move through a specific medium in relation to how fast it moves through a reference medium. Okay. Now, the reference medium could normally be air or vacuum, or and the other medium is normally a solution. It could be an organic solvent, it could be water, it could be your sample dissolved in the organic solvent or water. Okay. Ri value is dependent on temperature of the medium and the wavelength. Okay. Standard wavelength that is used is normally 589 nanometers, and standard temperature in air would be 20 degrees, okay, and 1013 pascals, okay, and 50% relative humidity. So normally, if we test a refractive index, these are the standard conditions. So let's start with what is the principle of refractometer. So basically, if you can see in this image, the light is incident on another medium. It is first passing through the first medium, which is air, and then passing through the second medium, which is water. So there are two phenomena. There is reflection and there is refraction. So what is the difference between the two? Refraction is when the light enters another medium and bends slightly. It would not go directly as a straight line. So the bend is normally measured as angle of refraction perpendicular to this medium. Angle of reflection would be when the light is reflected, as clearly you can see in this image. Okay, and this principle of refractometer is normally based on Snell's law. Now let's discuss the operating principle of a refractometer. So what are the instrumental parts in a refractometer? Okay, if you can see here, a beam of light from an incandescent lamp will pass through an optical mask, okay, or a condenser lens. Now this mask will basically confine the beam to the region of the cell. Okay. The lens will collimate the light beam, which passes through both the sample and reference cell. Now this would be a cell divided into two. So it would be a square with a slit in between. Okay. The sample cell will have its own independent inlet and outlet, and reference cell will also have its own independent inlet and outlet. Okay. Now the light beam would pass through the sample cell. Okay, sample cell and reference cell both, and basically be reflected back from this mirror. It would be reflected back through the sample and reference cells, okay, and via a zero glass, which basically affects the path of the light beam. It will fall on the diode or the light receiver. The light receiver has two diodes, each of which will produce an electrical current proportional to the amount of light that falls upon it. Initially, both the sample and reference cells are flushed with the mobile phase. So basically here I am talking about a differential refractometer or a refractive index detector, which is basically connected to an HPLC system. So in an HPLC, the mobile phase would pass through the column and enter into the detector. In the detector, it will pass through the sample cell and reference cell. So we need to ensure that this reference cell is filled with the mobile phase completely. There is no air bubble in this reference cell. Okay, so that I get accurate results. The reference cell, after it is flushed, is closed, and now sample will only pass through the sample cell, or basically the mobile phase, or whenever the sample enters, comes, elutes out of the column, would enter the sample cell. The refractive index of the mobile phase in both cells is the same, and position of the zero glass can be adjusted so that the detector is in optical balance with an equal amount of light falls on the diodes. When the sample elutes from the column into the sample cell, refractive index of the cell contents will change. This change in refractive index will deflect the light beam as it passes through the flow cell. Okay, so here the refraction phenomena will take place, and the unequal amount of light would basically fall on the diode. Okay, the change in current from the diodes that causes is amplified and used to basically produce a calibrated detector signal. This signal is expressed as nano refractive index units. Okay, and this corresponds to basically the difference between the refractive index of the sample and the sample cell and the mobile phase in the reference cell. Okay, if you can see here, this is how actually everything is placed in an RID detector. So let's talk about important factors that are affecting any refractometer or any calculation with a refractive index detector. Of utmost importance is your wavelength. Okay, wavelength has to be kept constant at all points of time. Okay, second most important would be your density. The density of a medium would directly affect the following parameters such as composition, temperature, and pressure. Now, temperature is of major influence on a refractive index and must be precisely controlled during the measurement. Any changes in the temperature during measurement will cause it wrong results. Okay, will result in your negative results. Temperature changes would also affect the sensitivity of the detector. Okay, and might be giving even invariably spikes. Now, older systems were often used with water bath for this purpose, but newer systems, all the latest systems now available in the market, have an option to control this temperature with a Peltier heater. Okay, so a Peltier temperature control is available. This high precision temperature control would stabilize the temperature in both the sample and reference cell. Not just that, you also need to control the temperature of the mobile phase flowing through this detector. If that is not controlled, again, the results would not be as per expectation, or there might be some drift in the detector, baseline drifts. So a column oven has to be maintained here. Nowadays, even heat exchangers are available to control or to maintain the temperature of the mobile phase. So after the pump, before entering the column, the mobile phase is preheated in a heat exchanger. Then it enters into the column, and at that temperature, same temperature is set at on an RID detector or a differential refractometer. Okay, so the temperature has to be kept constant, either it is the column oven or the RID. Even the composition of mobile phase has to be kept constant. I cannot change my diluents, I cannot change my composition of mobile phase, which means I cannot do a gradient analysis when I'm using an RID detector. It is also always has to be in isocratic mode. So this is actually one of the limitations of analyzing or using an RID detector, that you cannot do any gradient separation. Whatever separations can be done, it is possible only via isocratic mode with constant temperature. Okay. So let's discuss some applications, very important applications of an RID detector. Now, what kind of samples are basically analyzed using such detection technique? Samples which cannot be otherwise analyzed by an alternate detector such as a UV detector or an FLD detector or any other sort of detectors commonly used in the lab. And those compounds which are not having a chromophores or a UV absorbing capabilities are normally analyzed by an RID detector. The most commonly tested product with a refractometer would be a carbohydrate analysis, sugar analysis, right? Organic acids. Normally, RID detectors are said to be universal detectors, and it is true. It would give you a response for anything that is injected onto this detector. The only drawback would be sensitivity. The concentrations that I have to detect using this technique should be very high. How high, that we would know when we determine the limit of detection of my particular sample. It may vary from sample to sample. It may vary from your diluent to diluent. It may vary from mobile phase to mobile phase. Some temperatures might give me better results. So all the parameters need to be optimized before analyzing this. Now, RID detectors are also commonly used in polymer analysis in GPC and SEC. So basically, size exclusion chromatography column can be connected on an HPLC, and polymer analysis can also be done using an RID detector. What information this RID would give you is basically information regarding molecular weight of the polymers. So RID can also be used for such applications. Let's discuss in detail some of the applications of HPLC using an RID detector. So if you can see over here, fruit wine analysis is done on an RID detector. The separation is done using an Agilent high-plex CA column. Okay, this is basically a ligate exchange column which would enable separation of sugar molecules. The mobile phase would be 100% water. Normally in ligand exchange columns, the mobile phase is kept constant as water or maybe any of some buffers with certain molarities. Flow rates are also maintained at less than 1 ml. High temperature analysis is performed normally for these kind of applications. So temperature is kept quite high at 85 degrees, and maybe refractive index temperature would be maintained at around 55 degrees, which is the maximum. If you can see, all the sugars are very well separated. This is a chromatogram of a sample of fruit wine. Of course, for analyzing this kind of analysis, you need to inject standards first, develop the method using the standards of the analytes that you want to detect, and then inject your sample. Comparing the areas of both the peaks, for example, if I inject a standard of glucose, I need to compare the area under the peak for a known concentration of standard, and I can find out with the help of area under the peak of the sample that what is the quantity of glucose in my sample. So qualitative, quantitative estimations can be easily done. Linear graphs can be plotted. That means I can perform a calibration of standards, and with the help, so this detector is a linear detector. So it would directly be able to give me the concentration of any of the analytes. Next application, again, a very common application would be sugar analysis in fruit juice. If you see, all these analysis of sugars are performed on ligand exchange columns. Now, this kind of application is, I would say, an eco-friendly sample analysis or a green analysis, because here we are not using any kind of organic solvents. We are using 100% water, and the flow rates are also quite minimum, which is like around from 0.3 ml, 0.2 ml to 0.6, 0.7 ml flow rates at the max are used. Okay, so it's easy to do such analysis also because sugars would basically be easily extracted in my water samples, so I can keep the diluent as also as water. If you can see here, there are 4 chromatograms that are compared. So sugar analysis was done on orange juice, apple juice, pineapple juice, and tomato juice, and they were comparing the concentrations of sucrose, glucose, and fructose in these samples. Okay, so it's a very straightforward application, and not much map development would be required. So we have an application compendium for food analysis and sugar analysis on these columns, wherein all kind of sugars, oligosaccharides are tested on different type of columns using basically diluent or mobile phase as water or some buffers. Let's discuss the next application again on RID, which is oligosaccharide analysis. If you can see here, again, we have used a high-plex column with water. And if you can see, sugars, oligosaccharides from DP4 to DP9 plus were easily separated on this column. They're very well separated on this column. Flow rate is kept at 0.4 ml. So all these isocratic modes are very good and essential to basically test sugar analysis. It's quite easy to do sugar analysis with this kind of technique. One very unique application as well that we did on RID. So basically, inulin was sourced from some plant, and there was no standard available. And we injected the same on this RED detector and got a response, got a chromatogram. Now, we do not have a standard for inulin, so we could only do a qualitative estimation, but quantitative estimation could not be performed. However, there was a way out because refractive index detectors are universal detectors. They would give a response directly proportional to the concentration. The only thing that we need to ensure is proper separation. That means chromatographic purity, which basically means that if this is my inulin peak, it should be 100% chromatographically pure. There should not be any underlying impurities which is merging with this peak, which I cannot see. Assuming that is the case, we can just monitor the area percent and find out that my sample purity or my sample would contain around 92% roughly of inulin. Okay. So this is a very unique application wherein without the need for a standard, we could still find out roughly what could be the purity in my sample with the help of area percent. So this value is normally depicted in the software itself. I do not need to do any sort of calculations. Let's talk about florimetry, which is the last topic for today. Now, basically, florimetry is commonly called as fluorescence spectroscopy. Okay, and this is a spectroscopy that is used to analyze samples which exhibit fluorescence. Okay, now, and what is exactly fluorescence? It is basically a phenomena wherein a sample is irradiated with some light at a specific wavelength. The electrons in that sample would get excited and move to an excited state by absorbing that radiation. Okay. After a certain amount of time, which is very, very low, it would again try to come back to the ground state. And while coming back to the ground state, it would emit a certain radiation at a specific wavelength. That radiation we can see in the form of light radiation, right? And that is what is measured. And this phenomenon is called as fluorescence. So basically, emission of radiation when the molecules are excited by the radiation at a certain phenomenon is called as fluorescence. Let's talk about the Jablonski diagram. Okay, this is basically a very commonly seen diagram. If you find or if you look or if you search for principle of fluorescence and phosphorescence, this would be the first diagram that you'd always see. If the incident light at a specific wavelength where the molecule will absorb the photon, okay, the molecule is then excited from the electronic ground state to a higher excited state, which is denoted as S2. The electrons then go through an internal conversion. They are affected by vibrational and relaxation and heat loss to the environment. Okay, due to this, it would emit basically a photon, which we would see in the form of a radiation or fluorescence, sorry. In conventional fluorescence, photons are emitted at higher wavelengths than the photons which are absorbed. Okay, this diagram is extremely important when we want to understand fluorescence, because when venturing a fluorescence spectrum, one is typically looking at intensity at which molecule emits. Okay, the wavelength or energy at which it emits, and also the time which the molecule spends in the excited state. This time that it spends in the excited state is known as fluorescence lifetime. Now, this is a typical fluorescence spectra that we see. Normally, absorption spectra is not the one that we would be interested in. we would be interested in the other half of this, which is the transmission spectra. Okay. What information would the spectra give me? So if you can see here, there is a maxima. That means there was a particular wavelength which the compound emitted, okay, which is measured as a maxima. That means the maximum wavelength that it was able to emit. Each spectra is like a fingerprint to a particular compound. Let's see how this spectra would help us in my date sample analysis or checking my peak purity. So normally, if a fluorescence detector is connected to an HPLC, we get a chromatogram. Now, like I said in RID, it wouldn't be possible to know under the peak if there is any other impurity merging. So FLD basically is equipped with giving you a spectral data as well. So achieving a spectra, you can find out whether each individual peak is pure or not. This is a basically 3D plot of the same. So each peak can be seen from the top, and this plot basically helps you see each and every peak purity. All these peaks are currently seen as extremely pure. I cannot see any other peaks merging. Suppose, for example, if peak number 4 there was something merging, I would see two dots over here in the spectra. There is just one dot at this particular RT, which basically means that this peak is pure. Another way of finding the peak purity would be I inject a standard and I save the spectra of that particular standard, create a spectral library in my software. After the chromatogram, after the samples are analyzed, injected, and separated on the column, I can find out the purity of this particular peak or any of these peaks at different set of points. These points could be predefined, or the user could have an option to maybe measure the purity of this particular peak at say 5 points. One point could be selected as the base, second could be selected at height divided by 2, and third one could be selected as the peak apex, followed by again the tail, that means height divided by 2, and the at the tail base of this peak over here. So at 5 points I can find out the purity of the peak. What the software will do would compare the spectra of my standard, which is 100% pure compound, to the spectra of the same compound that I think would be my compound in the sample. So for example, if I want to analyze this particular compound, okay, or maybe chrysene, for example, the ninth peak, I need to inject the standard, save the spectra in the spectra library, then inject the sample. The software would save the spectra and compare the spectra of chrysene standard to that of my sample. So I would compare the peak eluted at 9 minutes to my standard of chrysene and find out whether what is the purity. Peak purity is normally calculated with a threshold of about 100%. So 100% would be the maximum purity of any compound. And I could have keep a threshold of maybe 90% or greater. So fluorescence spectroscopy basically is a very, very useful technique. It gives me information of chromatographic purity as well, and it's a very selective technique. So let's talk about essential components which comprise of a fluorescence spectrophotometer. Now, a fluorescence spectrometer basically consists of a light source. This light source is normally used as xenon flash lamp. Now, each flash from this light source lasts in the region of around 3 microseconds, okay, and produces a continuous spectrum of light from 200 to 900 nanometers. Okay, now this is followed by a lens. Now the radiation from the lamp is focused by the first lens and reflected by the mirror onto an excitation monochromator. What is an excitation monochromator now? This is also called as a monochromator grating. And the principle of this is that the radiation which is emitted from the lamp is dispersed and reflected by the excitation monochromator at a specific wavelength. So whatever wavelength that we want to give as an excitation wavelength, this grating would basically transmit this light that of at that particular wavelength onto the flow cell. Okay. Now the grating is normally controlled by a DC motor, and the position of the grating determines what wavelength is falling on the flow cell. Okay. This flow cell is quite simple. It would be made up of quartz. Okay. And the back pressure withstanding capability of normally quartz flow cells is quite low compared to your normal diode array detectors or your UV detectors. Okay. The light is now split into two after the flow cell. One is passing towards my one end of the light would fall on my photomultiplier and other would be on my photodiode. Okay. The fluorescence from the sample in the flow cell is collected at right angles to the incident light by this second lens, and it is passed through a slit, okay, on an emission monochromator. Before the luminescence reaches this emission monochromator, a cutoff filter removes the light below a certain wavelength. This will help reducing noise, basically, or stray light. The selected wavelength of light is reflected onto the slit in the wall of the photomultiplier compartment. Now, this grating is also turned using a DC motor. The position of the grating again determining the wavelength range. So we have to feed in an excitation wavelength and an emission wavelength over here. The photomultiplier will basically, what it will do is, it will duplicate or I would say amplify this data that it receives over here. Now, incident photons hit by the photocathode and generate what is called as electrons. These electrons now accelerated by an electric field between several arc-shaped diodes. Okay, depending upon the voltage difference, any pair of diodes one photon hitting the photocathode will produce many electrons, thus multiplying this signal. That is why it's known as a photomultiplier. Whereas the photodiode would work as a reference diode. Okay, this diode will measure the excitation light transmitted by the flow cell and corrects flash lamp fluctuations in long-term intensity. So basically there is an option of keeping a reference wavelength as well during your analysis. So we feed in an excitation wavelength, we should know an emission wavelength, and we can keep a reference wavelength so that any fluctuations due to the flam can be corrected. There shouldn't be any noise during my analysis, so that is reduced. Okay, the response of the reference diode is basically subtracted from the photomultiplier tube to give a flatter and less noisy baseline. So this is basic instrumentation of a fluorescence spectrometer. So fluorescence detectors are also called as FLD detectors, which are used in HPLC, and fluorescence spectrophotometers also follow similar instrumentation. Let's talk about some application areas, very important application areas of a fluorescence technique. Now, for what kind of samples of fluorescence would be tested? Normally, compounds which are easily fluorescing in nature, but the analytes that we normally test, for example, any biomolecules that we want to test, it's not necessary that they are fluorescing in nature. So what we can do is we can derivatize them. We can create a reaction. We can basically react those such kind of samples with a fluorescing compound like FMOC. Okay. Some important attributes to know before you decide to test any kind of sample using a fluorescence spectroscopy technique. These analytes should be UV absorbing. So it's not necessary that they should fluoresce normally, but they should be UV absorbing species. That means you should be able to detect these samples through your UV detector as well. Now, these analytes need to emit visible or near IR radiation. With fluorescence analysis, we can also do quantitative measurements. So this is also a concentration-based detector. It can be connected to an HPLC system, and multiple peaks in a chromatogram can be analyzed simultaneously. That means multiple analytes in a sample can be analyzed using this technique. What compounds, what samples cannot be analyzed? Of course, those that can undergo photochemical reaction at or above the wavelength of interest, which would destroy my sample. The sample should not be colloidal. It should be clear, transparent. So if required, I should be filtering my samples before analyzing them in the spectrometer or the FLD detector. Okay, so obviously compounds which do not show fluorescence are unsuitable. Let's talk about a very, very common application that is used in any food testing laboratory, okay, which is aflatoxin analysis. So there are several methods, several techniques which are available to do this, but the most standard protocol given is with an HPLC system using an FLD detector. Okay. Now, again, these aflatoxins are not very naturally, they do not exhibit some kind of fluorescence, but we want a better sensitive detection, which would basically be less than 1 ppb. Okay. So normally if I just inject aflatoxin or I inject samples which are containing aflatoxins in my FLG detector, I would get a response, but not at a very low concentration. I would get somewhere around 10 ppm concentration. But that is not the concentration that I need to test. My limit of detection would be less than 30 ppb, less than 40 ppb, or the whatever the standard that is provided by the regulatory authorities. Okay, so here this basically this analysis is used or is carried out using a cobra cell to derivatize my aflatoxins. Okay, so this cobra cell is basically electrochemical derivatization of aflatoxins. So the sample is injected as it is, and a post column derivatization is done using a cobra cell. Okay, so once all the aflatoxins are separated on the column outlet is connected to the cobra cell, where the sample, each and every individual aflatoxin will elute one by one. They would derivatize, undergo derivatization, and then enter into my fluorescence detector. So this kind of derivatization is called post-column derivatization. Apart from cobra cell, there is something called as Fred, which is also kept after the column. It is basically something, a small apparatus which is containing capillaries, okay, a very long capillary and a UV lamp. Okay, so basically that also can be used as a post-column derivatization unit. And over here, if you can see, there are four important aflatoxins, B1, B2, G1, G2, that are commonly tested in, here we have taken an example of peanut butter and corn. Okay, and the limit achieved, LOD, that means limit of detection achieved is 0.1 ppb in the standard itself, which is very good. This chromatogram depicts the corn sample and peanut butter sample, which is injected onto the same, under the same conditions. Okay, the method is quite simple. The column is normally used C18 column, and it is an isocratic mobile phase. Okay, so you can see all the four peaks well separated and detected as well. Okay, so you can compare the results with the standard injection. You can compare the area under the peaks and find out the unknown concentration of all the four aflatoxins. Okay, so you can do qualitative and quantitative estimation both from your samples. Next important application would be amino acid analysis. This is also very commonly used application or performed in any food testing lab. And fluorescence detector is commonly used because again here I'm looking for sensitivity. Fluorescence detectors are very sensitive compared to your UV detectors, and much, much more sensitive than refractive index detectors. So here, the samples used for amino acids, it could be your maize, it could be wheat flour, it could be rice sample, it could be any of these samples that would contain proteins. The samples need to be first hydrolyzed before injecting into an HPLC system. So you need to you need to put your samples in a hydrolysis tube. Okay, keep maybe add a certain quantity of acid in that to hydrolyze it overnight. You need to keep a certain temperature. After the hydrolysis reaction is completed, the samples are filtered. Then the samples are derivatized, because again here amino acids are not naturally fluorescing in nature. However, they can be detected by a UV detector at a certain sensitivity. So they need to be derivatized. Normally, after the samples are hydrolyzed, the derivatization is done externally manually. So we need to add, there are two reagents, OPA and MPA, that are added on in the sample to derivatize them. Okay, so that you can get a very good response in an FLD detector. You can have different kind of method chromatographic conditions. Okay, there are a lot of methods that are available out there wherein you can have separation of 20 amino acids, 22 amino acids. Like for example, this is a very good example where in 7 minutes time 23 amino acids were well separated and detected. This kind of sample was derivatized basically using online derivatization. So HPLC autosamplers are capable of dilutions, capable of programming. Basically, you can derivatize the samples in the injector itself. So for example, after hydrolyzing maybe 20 samples overnight, I just filter the samples and keep it in the vial in the autosampler. Once the vials are kept in the autosampler, I just fill my derivatization reagents in another vial and just program it in such a way that all my samples are derivatized one by one right before they are injected on the column. Okay, so it is a very good technique wherein all your amino acids can be separated in your 8 minutes time. Of course, this kind of analysis was performed on sub 2 micron particle size columns. So you need a UHPLC system to do that. However, you can do the same analysis on an HPLC system also using a C18 column. So this is a very good application wherein UV and FLD detectors sometimes are also used in series. Okay. So with this, we have completed today's session. So thank you so much, everyone, for your kind attention and for attending this webinar.